Okay, morning everyone. So we'll start off with a quick practice question, just see how you do with cyclic compounds and drawing different diagrams. Slowly we're seeing the pieces fit together here, so we'll just do this here for a while. This one here, I'm actually going to condense the structure for you, CH2F, CHCl2. First thing I would encourage you to do for that one is see if you can draw out a diagram, find out what the parents are, find out what sort of branches there are. Once you sort of get a diagram for that, the naming part will be a little bit easier. And just practicing of another compound here, let's do 2,5 dibromo, 3 ethyl, and let's just do a hexane. Okay. Up to this point, we've just been in the alkane family. Everything is just single bonded. After we go over these questions here, we'll steadily look at different families. So again, I encourage you just to pause the video so you can just give a chance to try it out. Assuming you've done that here, you can just check your work with me here. So this first one here, evidently being a condensed structure here, looks a little bit scarier. Let's start off with what we know. So most organic compounds here are built off of carbon. So I just circle those two carbons there. Even though they put all these H's and F's in between, I know those have to be terminal. These H's here are very likely connected to each other. And again, up to this point, we've just been assuming things have been single bonded. Okay. Now, as we break it apart here, normally for carbons, 4 unpaired electrons. If we don't specify that it's attached to a carbon, it would normally be holding 3 hydrogens. You notice this carbon here still has 2 H's, but one of the H's has been substituted with the F. It really doesn't matter where you put the F. We're going to see here single bonds here twist and rotate no problem. Okay, so we're starting to get the structure here where it would have been CH3. One of the hydrogens was replaced by a fluorine. Very similarly here for the second part, I would be expecting another CH3. The carbon here can hold 3 other attachments here. I would have expected most of them to be hydrogens, and yet they tell you, with the exception for one of them that's an H, the other 2 are Cls. And again, it doesn't matter where you put the ending up Cls. Nice thing about IUPAC's naming here is you'll end up with the same name regardless of where we put those Cls there. So, done the hard part there from the condensed formula here. We'll start off with our parent. Our parent here is just made out of carbon. So again, even though Cl here does look like it starts with that C there, it's not a carbon. That's just a halogen. It doesn't extend the backbone or anything like that. Here we have a parent that's fairly short. It's just 2 carbons. So the prefix is going to be eth. We see everything is all single bonded. So ethane is our basic structure here. And then in places of these hydrogens here, we've substituted on a couple different groups, fluoros and chloros here. We see that this carbon here on the right-hand side actually has 2 of the attachments, so we probably want that to be carbon number 1, the other one here to be carbon number 2, and with that, with just alphabetical here, C for chloro comes before the F, so we can go here 1, 1, even though both chlorines happen to be on the same carbon here, I still double up the number there, 1, dichloro. The dichloro tells you that there's 2 chlorines somewhere in the picture. Turns out both of them are on 1. The fluoro is on 2, so 2 fluoro. And again, in general, we usually ram this last branch here into the parent name. We are based off a 2-carbon single bonded family ethane. So 1, dichloro, 2 fluoroethane. For this other molecule here, again, generally I find this to be a little bit easier when we already have the name. We're just trying to draw the structure. Start off with the very ending of the name. So this one here, they're telling you is hex. So we're looking at 6 carbons in a row. Because it's totally up to us how we do this counting here, let's just count it left to right. Every carbon here should have the equivalent of 4 unpaired electrons, 4 different bonds. Most of them are saturated with hydrogens. We're going to, in place of position 2, position 5, there happen to be bromines instead. So position 2, again, doesn't matter whether you put the bromine on top or bottom. The most common problem I see people do is they see the dibromo, they recognize it's 2 bromines, but without putting one of them on 2, one of them on 5, they may accidentally put both on the first carbon there. So in that case there, that would actually need to be 2,2 dibromo. Because they're specifying directly where they are, 2, 5, one's on 2, one's on 5. Nicely symmetrical looking picture there. And then on position 3, we happen to have an ethyl group. Ethyl group here is going to be a 2-carbon alkyl branch, 2-carbon shoot off of this trunk here. So again, it doesn't matter where you put the carbons, it could be on top or bottom, but that should be 2 carbons there. It looks like the longest chain is going to be 6. If you were to draw a condensed structure or structural formula here, it may be good to actually include all the number of hydrogens. And again, how you're going to track the number of hydrogens is just, well, every carbon should make the equivalent of 4 bonds. If I see it's making 2 bonds, that means there's 2 extra arms. It's only using 1 bond here. It's 3 extra arms. I could condense it in that fashion there. So far, we've just been dealing with alkanes. Alkanes are said to be saturated. The word saturated means it contains the maximum number of substituents. It's holding the absolute maximum number of branches it can hold. As we saw earlier, we introduced a ring. We started losing hydrogens here. We slowly get degrees of unsaturation. Today, as we skip over from the alkane family over to the alkenes, we'll see another way we can actually unsaturate the compound here. It is where we borrow the word here, saturated and unsaturated fats. Okay, more on that in a second here. But nicely, all the naming, find the longest carbon chain, keep the numbers tiny, alphabetize the branches. All of that will carry over as we go over to these newer families. So we've done most of the IUPAC naming. All we're going to do is we're going to steadily change the family. And ultimately here, we're going to be changing the ending of this name here. Earlier, we were at alkane family, everything single bonded. Today, we're going to introduce the family of alkenes. So alkenes. Looks very similar to previous here, but the key difference here is instead of an ANE ending, it's actually an ENE ending. Most of you will remember that for alkenes, it is going to be a double bond, but I want to really specify where the double bond has to be is it actually has to be between 2 carbons. So towards the end of this chapter, we're going to double bond to oxygen, double bond to other elements. Those aren't alkenes unless the double bond actually comes between 2 carbon centers. Which means that the simplest alkene we can have, it can't be 1 carbon, or else I can't have a double bond in between. At the very least, I have to have 2 carbons. We start off from the saturated form here. This guy here is ethane. Everything is single bonded. Just like we saw happens when we form a ring, I had to ditch the 2 sides. I had to lose some of my substituents. I need to become unsaturated here. What's going to happen here is, if we just fast forward, if the carbon is supposed to make a double bond with the other carbon, that only leaves 2 extra arms on each of the carbon substituents here. Unless otherwise specified, you assume the other sides are going to be H. Okay? So, just like we did with rings here, we see this introduces a degree of unsaturation here. We're going to lose 2 H's per, we're just going to say in general here, multiple bond. So multiple bond here is, say, going from single to double bond. Tomorrow when we go to triple bond, we're also going to lose 2 hydrogens again. These are definitely not going to be structural isomers. They're going to have different molecular formulas here. In a saturated compound here, so far we had C2H6, so 2N plus 2. For us here, because we lost the 2 hydrogens, I have to lose 2 of the arms so that the carbons here have the 2 extra unpaired electrons just to hold each other with this double bond here. That gives me only C2H4. Now, that's the main difference here. The similarities here are more common here. Well, we're still a 2-carbon backbone. The prefix for 2 is still going to be eth, but now this is the first time we're actually changing the family name. We're going to change the suffix. So this little syllable that comes towards the end of the word here, we're actually going to change this here to ethene. All right? So that gives us a degree of unsaturation here, pretty much aside from saturated alkanes here. If we have less than the number of maximum substituents, right, I had to lose 2 of my arms just to hold the carbon neighbors together, we get degrees of unsaturation. I mentioned this is where we get unsaturated fats from. Turns out for saturated fats, fatty molecules here usually have a polar head. They usually have a really long hydrocarbon tails. Hydrocarbon tails we saw previously in the last chapter, they were nonpolar. They're really strongly held together, relatively speaking, with London forces. Turns out these saturated fats here are really hard for our body to digest because these are all really parallel, all really tied really tightly and closely together. Turns out as we start introducing a double bond or triple bond or whatnot, we introduce in this molecule here, most of the molecules are the same. We still have some sort of polar head. There's some detail there that I'm skipping over. But what we're going to do is, along some of these chains here, what we're going to start doing is we're going to start introducing, instead of being all single bonded, kinking back and forth, we're going to introduce, say, a double bond. And by the time we introduce a double bond, we're going to see that unlike a single bond, which can twist no problem, double bonds here are very rigid. Okay, they don't twist very easily. So let's say I happen to have a double bond here, and let's say it actually happened to kink one of the arms here down this way. Well, what's going to happen here is my chain here, they're no longer all very parallel here. It's introducing some geometry that causes some of these tails here to sort of bend away from each other here, and it does allow for bodies to sort of break down unsaturated fats a little bit easier. So if you have a choice, we try to veer away from trans or saturated fats, which are very hard for our bodies to digest, and we would rather have more unsaturation. Okay, so we've already seen a little bit of the changing in naming here. The ending of the naming instead of ANE, and now it's going to end in ENE instead. So let's just continue onwards here. Again, the group that sort of gave us these rules here, IUPAC, they sort of set all these rules. A lot of it's actually the same, but I'm going to emphasize the main differences here. Okay, so first step, same as usual. Let's find the longest carbon chain. This is going to be your parent, but there's a little bit of a caveat here. Because the double bond is so special to the molecule, later on we're going to call it a functional group, we want to make sure that this double bond is actually part of the chain. So find the longest carbon chain that contains the C double bond C. Okay, I want to make sure that that double bond is included in my longest chain. So hypothetically, I could have a really long string of single bonded molecules here. If it doesn't contain the double bond, that's not going to be our parent. Okay. The other thing that we're going to take note of, aside from the ending change from ENE, because this double bond here as a functional group is so special, we say the language here, the double bond takes priority. In terms of our naming, something that takes priority always takes the smallest number. So in our example here, the double bond, in general, we can say it takes priority over all the other groups. Okay, and you can translate that for yourself. This one takes the lowest number. If you're counting the chain and you're trying to keep the numbers tiny here, the double bond, it's kind of weird. We usually just use numbers just for branches, but this time here, actually the double bond itself actually has to be the lowest number. Okay, so let's start off with an example molecule here. Say I have C double bond C. I'm going to plop over a few different carbons here. Okay, should make it one step longer so you can sort of sway your vote a little bit. Okay. Same sort of story throughout this chapter. We're trying to do the naming. We're trying to come up with a unambiguous name that sort of fits this structure here, so that if I give the word name, you know directly what to draw. Well, following the rules here as we know it, let's find the longest carbon chain. So here doesn't look like we have any substituents, but we have all the carbons. Again, it is understood that everything else is saturated with hydrogens. So I'm just not drawing those H's because they don't really affect my name. Technically speaking, you might say, well, this 6 carbon chain here along the bottom is the longest chain. And I happen to have like a double bond that's sort of on the side there. Well, that doesn't follow this rule here where the double bond, the parent, has to be included inside the longest chain. I have not included this double bond here. So even though 6 definitely would be the longest chain, if I had to kink up one way or the other, it's at least 5 or 4. Because we don't include this double bond here, this can't be my parent. At the very least, we need to include this side. I want to make sure that that one carbon there is actually involved inside this molecule. Still, we try to maximize, we try to make the carbon chain as long as we can get. If I veer it this way here, I can get 4 carbons. Going this way here gives me 5 carbons. That is the longest chain that contains this as a double bond. So that's actually going to decide our parent for us here. We have 5 carbons in the parent, so our very last word is going to be pent something. Up to this point, we've always been saying pentane, ANE for an alkane ending. In this case here, we're actually going to be a pentene. Okay, it sounds like the shampoo there. Okay, so we have pentene, we have a 5 carbon, and we have a double bonded family in this molecule. It is totally possible that molecules can have many multiple bonds, many double bonds, many triple bonds. Every time I switch over to a multiple bond, I lose hydrogens. I get more unsaturation. But again, for simplicity for us, our parent has to include the double bond, and we'll only deal with molecules that only have one double bond. Okay, so we have the pentene here. There is little note here. Because the double bond here takes priority, just drawing 5 carbons in a row doesn't necessarily tell me where the double bond is. In this case here, I see the double bond stretching between, let's say, the first carbon and the second carbon here. Well, that double bond very much, it could have been between these two, could have been between these two, could have been these two. The double bond could have been anywhere along the parent. So just like we do with branches, I know this time we're looking inside the parent itself, I actually want to specify where the double bond actually starts from. The double bond does take priority, so even if later on, even if this guy here happened to have other branches and naming this one here being 1 would make the other numbers tinier, but that would make my double bond between 4 and 5, that's not as small as it could be with 1 and 2 here. So the double bond takes priority, it takes the smallest number. I see that my double bond here stretches between 1 and 2. This is a little bit weird, but we're going to put a 1 in front of the parent name. Sometimes even they say pent 1-ene. And what that says here is the ene part, the double bond, okay? The double bond starts from, I know it stretches between 2 carbons here, it starts from carbon number 1. So it starts from C1. If this had been 2-pentene, all it does here is it moves the double bond along. This double bond here takes priority. It takes the smallest number. Even if I happen to have fluorine groups later on, oh shoot, that's going to be a lot of 5s. So be it. Those are going to be 5s, okay? The double bond takes priority. That takes the smallest number. Okay? So we've seen a couple things now. We've seen how our parent has to include the double bond. The double bond has to be the smallest number. It takes priority. Now having this as my longest parent, turns out that this one here is going to be an offshoot. It's going to be a branch, an alkyl group. That branch by itself has 2 carbons, so that's going to be an ethyl branch. That's still branched off carbon position number 2. So this part here is normal, what you're used to, 2-ethyl, 1-pentene. Okay. Earlier I didn't have the fluorines there, but if you really wanted to add the fluorines, right, that would have been fine without the Fs there. Even though the fluorines here are all on this carbon, treating this as carbon number 1 would have been nice. Because the double bond was more special to the molecule, I'll leave it at 5. There's 2 of the same fluorine groups here, F for fluoro, so that means the F should actually come in between here. I might have a 5,5 difluoro. Okay. So most of the naming we've seen before. We've seen the alphabetizing E for the ethyl. I have 2 of the same group as difluoro, but I still alphabetize it with the F. Okay. Anytime you have numbers and numbers, they're separated by commas. Numbers and letters are always separated by a hyphen. Okay. So most people, when they look at this, are like, oh yeah, I sort of get it, right? So the parent has to include the double bond, it has to be the tiniest number. What they start thinking, though, is, okay, well, the tiniest number then would be a 1, wouldn't it? Well, it turns out, especially for parents that are very, very long, the hexane, heptane, and whatnot, the double bond can be anywhere mid-chain. So let's pretend here to have a slightly larger molecule. So let's do the same sort of little analysis here. I'm going to make it a little bit longer. I'll throw on a few other subgroups so you can sort of get some sense of practicing this. So let's make it here. Maybe an iodine group, maybe a C group. Maybe I'll put an H group over here. You can think about that. Okay. All right. But let's say I wanted to name the structure. Okay. All right. So let's find the longest chain. We see the fact that there is at least 1 double bond. So we know we have a degree of unsaturation. We're not holding the maximum number anymore. The double bond has to go through this, the parent. So that means our parent has to go this way. But most people get this mistake here and they say, well, the double bond takes priority. Couldn't I start the parent here? So that the double bond is like carbon number 1, 2. And that could just be a methyl group. Well, when we were counting our longest chain, we were allowed to start from any side to any side of the molecule here. This carbon here isn't the side of the molecule yet. So even though, yes, the double bond should take priority, it should take the smallest number, I can't start the parent here. That's already sort of mid-chain. At the very least, I need to start the parent, including this carbon here. So that is the side. And yes, I do have to go through the double bond. You can then sort of count the chain here. Should it go left? Should it go right here? Should be pretty obvious here. We're going to actually go to the right. So let's see if we can get the very last word in the name first. So in the parent, I have 1, 2, 3, 4, 5, 6, 7, 8. So the prefix is going to be oct. We're in the alkene family because we're a double bonded family. Again, we only have 1 double bond here. And having the double bond take priority, meaning I should actually count my 8 carbons. I'm still going to count to 8. But you notice the double bond starts from 2 to 3. That's as tiny as I can get it because this carbon here isn't the side of the molecule just yet. Because the double bond starts from position number 2, I could call it 2-octene. More often, though, I actually put the number here in between. So oct is going to be a parent, 8 carbons. Starting from position 2, there's an ene. Starting from position 2, there's a double bond that stretches over to carbon number 3. So whether you put the number in front of it or in between, that's totally up to you. But definitely the double bond tells you along this 8-carbon long parent, the double bond actually comes in sort of mid-chain, and that is the tiniest number it can actually show up. So octuene covers the parent that I've circled for you there. We have a bunch of other groups here. Well, this is a 1-carbon branch. That's called a methyl group. Oh, this is a 1-iodine branch here. This is called an iodo group. Remember, if it's a carbon group, it's understood that there's extra hydrogens. If it's a halogen, there's no other ones there. What about these H groups? Now, before you come along and start saying 4-hydro and whatnot, if you think back, wait a second. Even though we've only been drawing the C's, I had been assuming the back of all of these here had been H's anyways. So they were just trying to trick you a little bit here. They're making the H look like a substituent, but really we haven't subbed on anything different than it was there anyway. So in this case here, we can actually treat this one here, well, that's a 3-carbon branch. This hydrogen here would have been on anyway, so that really doesn't matter to our name at all. And now we just need to alphabetize here. 3 was propo, we have a methyl, we have iodo, so iodo comes first. I had to count the number top down, so the double bond occurs smallest. So just based on the alphabetizing, the first group here, which was iodo, happens to be at position 6, so 6-iodo. My methyl group is on position 5. And then we happen to have a 3-propo group. Again, very often they ram the very last name with the parent name. If you don't like that, you can put a hyphen in between. That's fine as well. Okay. So I want to just emphasize a lot of this is actually familiar to you. You know most of the alphabetizing, keep the numbers tiny and all that. And all we're really switching on here, we're now going to have a number, not just for branches, but the number for the double bond itself. And I always give you the smaller of the two numbers there. Okay. Let's try out another molecule here. It's possible I can have both ways of unsaturation. So maybe I have an unsaturation because I'm a ring. So let's say we have this one here. Okay, let's sub on a few different groups here. Let's put a chlorine. Let's put on maybe a fluorine over here. Okay. So this has both forms of unsaturation. The ring had already made me lose 2 hydrogens. Now having a double bond makes me lose yet another 2 hydrogens. We're going to only deal with molecules that only have one ring. The ring by itself inside is actually going to be the parent. Our ring here happens to have 5, so 5 is going to be a pent. Now, because this one here is not a pentane anymore, it's not a single bonded, we're now pentene, like we did earlier. We usually would put position number 1 where there's a branch, but again, because the double bond is the special functional group, it takes priority. Your choices really are limited to either I count 1, 2, going around this way, or I count the opposite way here, 1, 2. Those are the only ways to count this molecule because the double bond is more special. Okay. Now, in some molecules, you may even be tempted here. Couldn't I say, like, start off with 1? Oh, there's a branch over here already. Couldn't I go 1, 2, 3, 4, 5 like that, where I'm assuming the 1 is the tinier number, but then at least the branches are tiny? No, the double bond has to, even though I'm only giving you the first number, it has to stretch between that number and the next one. So our choices with 1, 2 stretching over the double bond here. If I counted the red way, the double bond here would start from 1. So this would be a pent-1-ene, or 1-pentene if you like. As I count it clockwise here, we're going to have a branch at 3 and 4. If I count it the other way, then I have one at 4 and 5. While 3 and 4 keeps the other numbers tiny. If I have a choice, I'd rather keep the numbers tinier as well. Okay. Now here's one reason why we typically put the number right before the ene part. If I just wrote pen-1-ene, I just have a long chain, so 5 carbons straight just across like that. Remember, if something is cyclic, we have to introduce that prefix here, cyclo, before the name. So our parent is a cyclo pent-1-ene, 5-carbon ring, where a double bond starts from position number 1. And the range of it is just labeling your branches here. C for chloro comes before the F, that's at position number 3. So 3-chloro with the 4-fluoro. Cyclopent-1-ene. Okay. So the name is steadily starting to get longer and longer, but there we go. Steadily bigger family. We start changing the suffix, and we also have a position to tell you where that happens. Okay. Just to finish off our alkenes here, this actually gives rise to one other type of isomer. Earlier we saw structural isomers where we started chopping the long chain, starting to reattach things, trying to get a different name for a different molecule. This time, the other type of isomer we're going to look at is going to be referred to as a geometric isomer. There's something about the geometry that's the same. So again, we start off with what we know, which is iso. This prefix means something is similar or something is the same. In our case here, exactly like a structural isomer, these ones here have the same molecular formula. They're going to have the same numbers of C's and H's and whatever number of elements. It actually has the same arrangement, the same structure. So this time we're not taking off a methyl group and trying to re-glue it on and whatnot. But these guys here being isomers, they have to be different in some way. What's different about them is, sure, you can say the geometry here, but we're just going to say they have some different orientation. They look different in 3D. And the question here is, well, how is this possible? Why is it just strictly for alkenes? Let's look at a simple example here. So we have an alkene family here, C++C. We started off having just sort of all hydrogens substituted and whatnot. This time what I'm going to do is I'm going to sub on, let's say, 2 fluorine groups. Okay. See if you can name this for me here. The name part just comes from the carbon bit. Okay, so it doesn't include the fact that there's fluorines, those are branches. We can add those substituents on. This is a 2-carbon molecule. So eth is going to be a prefix. You could technically call it eth1ene. But being such a short alkene here, just having the 2 carbons, if you already tell me you're in the E family, again, chemists are lazy, every now and then they might drop a number, okay? Because if you draw 2 carbons that have to have a double bond inside it, that's the only position it could go. Same thing for branches. Every now and then you see sometimes in the worksheets, they may actually drop a number or 2. It's only because there was only one way to draw that position, so they can drop the number. It's not wrong if you keep the number there, but again, if you can sort of save yourself some writing, we'd like to do that. Okay? So we have this molecule here, eth1ene, 1,2-difluoro, eth1ene. Okay? I want to ask a question here, drawing it one way like this, where the hydrogens are on the same side, or hydrogens are across, are these the same or are they different? Okay. As we were doing structural isomers, what we were doing is we were actually physically reacting and chopping off fluorine groups and moving the fluorine around. When I look at this, they actually look a lot more simple and a lot more similar than I'm expecting. We have both carbons, they have an H and an F, H and F, this one also an H and F, H and F. The only difference is the direction that the hydrogens are pointing. The hydrogens on this side are both pointing, let's say, upwards. On this side here, the hydrogens are pointing across from each other. Now, we didn't have this form of geometric isomers when we had alkanes. Alkanes, if you remember, we had a single bond. If you really wanted to have the fluorine on top and the hydrogen on bottom, all you would do is you would just twist the single bond. Single bonds here allow for free rotation, no problem. More on that in a later lesson. A double bond, however, like we alluded to earlier, the double bond is rigid. And being rigid means it doesn't twist. So not impossible to twist it, but very, like for this double bond here to stay the way it is, to stay intact as a double bond, it really doesn't allow this to actually twist. So it's not as simple as, oh, let's just flip this down here, and then we're the same molecule. Because a double bond, even when we do alkynes tomorrow with triple bonds, they also don't twist. They give rise, possibly, to these geometric isomers. Now we'll see another reason why alkynes don't have it, okay? But what we need to do here is we need to have some way distinguishing what if the hydrogens are both pointing the same direction. They can be both up. In this example here, my fluorines are both down. We say that they're on the same side. So same side of the double bond. So both up or both down like that. We're going to call this one isomer here, we're going to call this the Cis Isomer. So CIS. And this is going to be a prefix. This is going to come right in the beginning of the name. This is the cis kind of alkene because this happens to be on the same side. Now, your workbook here has a lot of little acronyms for yourself, memory aids and whatnot. Sometimes they like, cis is on the same side. Okay, they all just sort of sound the same here. They sound like S. Okay, cis, same side, pointing the same direction here. Somehow remember for yourself here, cis means same direction. While on the opposite side here, because the hydrogens are across from each other, one points diagonally up, one points diagonally the opposite way. Like in math class here, this would be a transverse. A transverse is a line that sort of cuts across the molecule. It's a diagonal. That actually stands for opposite side. All right. So just for alkenes, you may have possibility for cis and trans. If I actually have more than 2 substituents like this, we may even be more than cis or trans, but for the time being, we'll just look at cis or trans that way. So how is that going to look like here? Most of the word name will be exactly the same. We are an ethylene. We happen to have fluorines on both of them. So both of them are going to be 1, 2. We have a difluoroethylene. Okay, so that's going to be the basic structure. But knowing that we are an alkene, if you can identify for me which side those fluorines are on, if it were the guy on the left side, I'd start off with cis hyphen all of this that comes afterwards. If it were the guy on the left side here, it would then be trans hyphen all of this afterwards. Just like structural isomers, if it has a different name, it's a different molecule. Okay. So just look out for cis and trans specifically for a double bonded molecule. Let's just try an example here. We'll end off with this one here. Let's go 1, 2, 3, 4, 5, 6. Sure. Okay, so 8 carbons in total there. Okay. And let's just put a hydrogen on this side and a hydrogen on this side. Okay. Same sort of example, just name this molecule. Okay. We start off finding our longest carbon chain. So start from any side to any side. We start sort of linking our chain together here as carbon from one end to carbon on the other end. We're going to want to count it, so the double bond is the smallest number if possible. So in this case, you're counting it top down, 1, 2, 3, 4. The smallest position this double bond starts from is stretching from 3 over to 4. So it's going to be a 3. And what we are is we're based off an octene. So the very last word in our name is going to be something oct3ene. Okay, no cyclo because we're not a ring. And knowing the fact that alkenes very often they show cis or trans isomerism, they show those 2 different types, we want to specify at the beginning, are we the cis drawing of it or are we the trans drawing? Now earlier we actually had the hydrogens were similar and the fluorines were similar. This time is actually different. How you identify cis or trans, what we're going to do is we're going to specifically look at the carbons involved in the double bond. We're going to look at what's attached to them. So both of these carbons are holding a hydrogen. They have that hydrogen in common, and those hydrogens are across. Even though these other groupings here are not the same, this is a 2-carbon chain, this is now what looks like a 4-carbon chain afterwards here, those 2 are different, but at least the 2 similar groups here, so the 2 similar groups are across the double bond. They usually just look out for the hydrogens because very often it is just going to be an H here. Okay. Because they are across, this is going to be the trans isomer. We're going to put the prefix here, trans hyphen, before all this oct3ene. If I had cis oct3ene, all that would do is it would swap the hydrogen down here. That is a slightly different geometry, a slightly different 3D than the molecule that I've drawn here. Okay. It is possible, again, just for you to think about here, it's possible that I can have 4 different groups. Let's say I have a fluorine, bromine, iodine, chlorine, like that. When I start looking at the 2 carbons involved in the double bond here, I don't have 2 of the same group. So it's a little bit trickier for me to find cis or trans. If you go on to organic chemistry a little bit more in university, what we're going to start doing is we're going to start, even though these groups here are all different, I don't have both holding a hydrogen or both holding a fluorine and whatnot, we're actually going to prioritize. We're going to say, well, just based on atomic number, bromine has a higher atomic number. Between iodine and chlorine, iodine has a bigger atomic number. Even though bromine is different from the iodine, because the higher atomic number, the higher priority groupings are across from each other, this one acts more like the trans than, say, the cis, and that's where we actually use lettering here, EZ notation. But for us, just watch out for, it's possible for a double bonded family, alkene family, to have cis or trans if I have the similar group, if they are on different sides. One last point here. Because we assume the rest of the carbons here are holding hydrogens, there's no trouble of you writing all these hydrogens because all these other carbons are holding hydrogens. While these are all single bonds, they all twist and they all rotate no problem. It is a little bit problematic if instead of actually literally drawing out the H, if I condense that H here, I don't really know whether that H here is above or whether it's below to make it the cis or trans isomer. So just look out on your worksheet here. Specifically for the 2 carbons involved in the double bond, they should specify exactly which way those two hydrogens are pointed, if they're across, trans, if they're on the same side, cis. Right? So I'll leave it off there. If you have any questions, just let me know. Thanks, guys.